All right. Hello, everyone. My name is Laura Schulz. I'm the head of quantum computing at the Leibniz Supercomputing Center. I'm also have a lot of activities in strategic development for the overall supercomputing space, and I'm fundamentally, or from my earlier career, very much an HPC person. I've been listening for the last several hours to several of your presentations, and thank you to the organizers to inviting me to this. This has been very interesting and a bit of a different perspective. What I'm hearing on energy efficiency, and it's really interesting. So I think I'm going to be a little bit different in my approach, but I hope it resonates and connects, and that we can have an interesting conversation here. So the last thing that I want to say is I am sorry that I'm doing this digitally. I have been called back to the U.S. for a family medical issue, which is also the reason that I couldn't present this morning. So thank you to the organizers to bearing with me, and then also still including me in this event. So again, we're going to talk a little bit about energy efficiency, and I was going to give a perspective from the HPC side, some things that I've seen or see now as quantum is now coming in, and now that I'm wearing this quantum hat, bringing this technology into the HPC environment, how I kind of see things. Yeah, so next slide, please. For those of you who may not be familiar with the Leibniz Supercomputing Center, I am not sure where this event is happening, but if you're on the research campus out in Garching, then we're just right down the road. That is our building here in the lower frame of the picture. We have been around for about 60 years out at Garching for about somewhere around 20 or so, maybe a bit longer than that. We have about 300 employees. We continue to grow the quantum department itself. The brand new quantum department brought in 35 staff, and that's growing as well. We have one of our main reasons. We are an IT service provider, and we're a service provider for the Technical University of Munich, for the LMU. These are universities of excellence. They're very large, have quite a bit of compute needs and resources. We provide a lot of those services. For them. We also take care of several Bavarian entities, including the state the state library collection, several universities, Hochschule. Kind of our reach is fairly broad within the Bavarian state range. We are also one of the three major supercomputing centers within Germany. So there's us, there's HLRS in Stuttgart, and then there's Jülich up in the Aachen area. Now, the three of us, we rotate distribution and procurement of supercomputing systems. So we basically procure one after the other, kind of in a chain, in order to be able to provide our users with the most recent and technologically advanced computing offerings. And then at the European level, we are a hosting site, and we provide European science users or scientists with access to our system. So we kind of have a breadth, we got breadth abroad and regional, from state up through European. Next slide, please. So as I mentioned, we do several things. So we're going to be talking about supercomputing and quantum computing today. But as massive as that effort is, it is a part of our portfolio. We're also responsible for the network, the scientific network, the data movement and communication throughout the Bavarian ecosystem. So I guarantee that you are using the Munich Science Network probably right now. We do large-scale data storage. We have massive digital archives. We also store, for example, the satellite data coming from several satellites from the DLR as part of our terabyte project, and make that available for localized compute. We have virtualization and visualization capabilities to move data from zeros and ones to graphical visual representation and for analysis. And then we also do several things with training and education. And then on our staffs, we have, easily 30 plus PhDs that are domain experts themselves, and that have come into the Supercomputing Center to work very closely with the resources to do capability development, to provide new tools, new ways of compute with wearing the hat of the domain user, and then actually being able to be a bridge or a Sherpa for those domain users in the universities, for example, and connecting them very closely to the hardware to be able to understand really how to tune it and use it to the best of their science. So that kind of gives you an overview of what we do. And now I'm going to go in a little bit into HPC specifically. So if I could have the next slide. Okay, so this is a picture of our compute cube. This was a couple of years ago when, as I kind of mentioned, we do rotation of systems. This is when our main compute floor was completely stacked. This looks a little bit different now because we retire systems after a good 6 years or so. These systems, with the development and the evolution of the technology, it becomes more expensive, less efficient to operate them. The technology advances pretty quickly. For example, in that back half of that picture, you have our our initial SuperMOOC system that was, I want to say it was around 2.3 petaflops, somewhere in that space, took up the entire back half of that cube. It was replaced by the system up in that upper right-hand corner, which was SuperMOOC Phase 2, and we got 3 times the compute for about a third, or sorry, excuse me, twice the compute for a third of the footprint. And then what you're looking at in the foreground here with these nice green cables, this is SuperMOOC Next Generation, or NG Phase 1. And this one is about a 19.7 petaflop peak system, and for about the same energy. So we consistently increase our number of compute, decrease our footprint. So this is so HPC is a rapidly developing field of its own. A lot of times there's, especially in the quantum space, there's the perception that HPC has been figured out or is a commodity resource at this point, and that is true for a certain perspective or a certain part of data center type operations, but the type of computing that we do and the advanced architectures that we work with in something like a supercomputing center are definitely anything but commodity stagnant resource. Next slide, please. Okay, but I want to go back a little bit in history just for a bit, because I was chatting via email with Emily, and she was asking some fantastic questions, and so I was trying to address some of those. And I wanted to give a little bit of perspective of the history of supercomputing, kind of as related to energy efficiency. And the last speaker had made a really good point with saying that, that energy efficiency was kind of late to the game for technologies, for other technology waves, and that, looking at quantum now to kind of basically be born energy efficient. And I like that concept, and I think that that's true to a very large extent. The early supercomputing phase, I'm going to say the 1960s to the 1990s. There's a picture here from the last supercomputing conference where they found a Cray 1 system, and I absolutely adore these systems because they had kind of this party couch look to it, and but this was one of the early systems, and it is really true. When this technology came in, when we started to understand how to build larger like mainframe type systems, that the focus was on performance, and energy efficiency wasn't really even considered. In terms of cooling, there was some cooling that needed to be done. Early vector processors, like with this Cray system, was done with Freon, among some other technologies. And the machines, so basically the machines, they were developed, the computing was going on, and what really kind of hit an inflection point for this was when in the 90s, the US and Russia signed a nuclear treaty ban, and that meant that that missiles, or that nuclear warheads or nuclear experiments, could no longer be conducted to secure information on the operations. Warheads could no longer be tested for validity and viability, and with that ban, it caused a paradigm shift in computing, to be sure, because while both countries, frankly, were looking to have to ensure that these options were available, regardless of what you think about the nuclear arsenal, the concept was challenging in that you had systems, you had a nuclear arsenal that could not be tested and checked for operation viability, but yet the nations had to ensure that they were operational if it ever came to be needed. And it's basically like taking a car from the 1950s and having to ensure that if you turned the key over on the engine, it would work, but you could never do it unless you absolutely had to. So with this, the whole realm of modeling and simulation and computational experimentation really took off in a way that we really a paradigm shift, that we had to start taking all of the data that we previously had. We had to start with ab initio physics experiments, taking natural observations of the natural world, putting that into equations, algorithms, program, do modeling and simulation, and then do predictive results past the data that we already had. So this really created a boom for advanced computing. And with that, systems got larger, as we determined across the board from the physics perspective. And then we went to the biological spaces. We went into computational fluid dynamics, engineering, applications for industry. As we started to develop this tool and we started to get better resolution, understanding more complex systems, getting faster results, we increased the compute, increased the sizing. And so with that, in the 90s, in the early 90s, the LINPACK benchmark had actually already been established in kind of think of the 80s, maybe even the 70s, from Jack Dongara and other folks. But in the 90s is where we started to get the top 500 list. So if you could go to the next slide, please. All right, so the LINPACK is a benchmark. This is really the benchmark boss, right? So this is something that twice a year at the supercomputing conference, at the International Supercomputing Conference, several systems worldwide submit their benchmark results for this LINPACK. So this is a dense linear algebra kernel code that is performed. Typically, what we do is when we buy a system, when we procure a system, we go through a delivery phase. And then from delivery phase to acceptance, we have what's called a burn-in phase. And this is where in-house we do a lot of experiments. We basically really try to push the system to its limit, to get it broken in, to identify any problems, to clear out any dead nodes, to make sure that the software is properly functioning. But we really try to push the system. And so the LINPACK is one of those that does that for us, to kind of really get it settled in and ingrained into the ecosystem. So the LINPACK has a very functional purpose, but on the other hand, the results of these LINPACK results, or excuse me, the results of these LINPACK runs have become not just a functional, but really a political one as well. A lot of decisions for funding are based on the LINPACK numbers. So I used to work with the Department of Energy in the US, and I can always say that one of the benchmarks was how are we competing nationally against other countries, like for example China. And then once I came to LRZ and I started working with other colleagues, and we had Chinese colleagues come and give us presentations, they would put up the LINPACK results of the American systems, and they were using that as the bar in which to compete against. So the LINPACK has had a lot of significance, a lot of importance, and this is really a performance metric. Now, we can say good things and bad things about the LINPACK. It has kind of steered some of our decisions for system design that may not have been the best options for us in hindsight, but this is kind of a historical perspective, so that's where we are. So can we go to the next slide, please? Okay, so now kind of the turn of the centuries, I'm going to say the early 2000s, and we kind of had a bit of a shift here. So these systems were getting much larger, and then energy efficiency. Basically, the systems were getting larger, but then we were starting to get the power bills, and in the U.S., this wasn't. I mean, I'll be really honest. energy in the US is definitely much cheaper than it is in Europe. With procurements, for example, procurements that we do, we get money for the cost of the system plus the energy for the entire lifetime of the system. And the energy bill can be a very significant portion of the compute or of the overall price tag. Anywhere from a third to a half, it can be pretty massive. And so we take energy extremely serious, especially here in Germany and in Europe. The U.S. there are nuclear power facilities. There's also a larger grid infrastructure, and so they've been paying attention to it, but but definitely Europe has been ahead in the necessity and the urgency of thinking about this. Now, this is though you're looking here at one of the systems within the IBM Blue Gene series line, and this was one of the first ones. This series was one of the first ones to start thinking about energy efficiency. Before this, it had been air cooled. And I think it was around, it must have been the IBM Blue Gene Q series. So this was the Sequoia system. And they were using water cooling. Now, kind of a funny anecdote, I was at Livermore when this system came in, and I remember just being very impressed with learning about the watering infrastructure, how all this was working, and being very impressed by this and thinking that Livermore was so incredibly cutting edge. But then I came and started working at Leibniz Supercomputing Center, and I went down to the IBM research facility down in Ruschlikon in Switzerland, and up there on kind of their proud board of achievements, they had a big article clipping about the prototype systems installed at LRZ for cooling infrastructure that they had developed with IBM together, LRZ and IBM. And so LRZ was actually one of the first pioneers in this space for energy efficiency and water cooling. Later, we started with cold. It moved then into warm water, I'll talk about in a moment. But this was really kind of one of the big shifts for cooling systems in different ways and trying to address the energy reduction needs that we had to reduce the price tag for one, the power bill. That was a big issue. Now, the other thing I want to mention is that there were two kind of different swim lanes, we call them, that was kind of the strategy at the time. One swim lane was to look at the development of multi-core processors coupled with the cooling technology, but one idea in order to increase output for the amount of energy that you're using was to go with many small cores. That was one big, strategic direction that was designed, from candidates like the DOE, because frankly, we had a lot of the money. We had a lot of money for these big procurements. And with that, we could actually work with the companies and demand things of those companies, demand them to go into certain directions to develop their technology in a way that we needed for our particular needs. Right. So then metric wise about this time, the Green 500, this was about, I think it was about the maybe early teens, 2013, somewhere in there, came into the standardized metric suite for supercomputers, and it purposely addressing energy efficient supercomputing, and then giving acknowledgement and ranking to those that were able to reduce the energy expenditure for the compute. So then this flops per watt became an important metric alongside LINPACK. In order to be able to assess the validity or to recognize the significance of compute systems. Next slide, please. Okay, so this is the Green 500. Again, this is an example. I have to say, I felt a little bit because I was using ChatGPT to ask them to generate a picture of a supercomputer for me that was ecologically more friendly, and it gave me happy little birds and daisies. So there's our computing resources for you. But you can kind of see that this right now, Jülich and in Germany is the top Green 500 system. It's a relatively modest system at 4.5 pflop. but it currently ranks as one of the top for energy efficiency. And and this is an NVIDIA system. I believe that NVIDIA, if I remember correctly, NVIDIA is maybe 5 of the top 10 right now. So they have the compute and the resources, not just the GPU parts, but some of the other elements that they're working on are beneficial to getting down that power cost. Next slide, please. Okay, so then kind of moving a bit more to where we are now, right? So now we're in the teens, in the 20s range. Kind of another big shift that's happened in this particular phase is that we've moved towards exascale class computing. So we were in the petaflop range, or the petascale range, excuse me. Now we're moving into the exascale class range. So that is doing floating point operations, 10 to the 18th operations per second. This we, and throughout our history, we have these threshold points that really push us in terms of the capability, in terms of the engineering of these systems. And this was definitely true for the exascale class range in the 2010 region to now. This was driven by the Department of Energy exascale computing program. And here is where we started looking at not just the CPUs, not just the cooling, but now we're moving into head-on into heterogeneous compute region. So we started incorporating GPUs, figuring out how to integrate them into the overall compute, working also with some other specialized accelerators. And so we were looking to improve the performance per watt that we have. So this is the second swim lane, part of the second strategic thrust that was defined, really in the early 2000s. This was the one with offloaded accelerated capabilities. Right. At the same time, again, seeing that that was not going to be enough. Well, actually, sorry, let me go to the cooling part. So then we moved from cooling with cold water to doing cooling with warm water. So then that reduced the need to chill the water. And by, the particular technology, you could run room temperature water through a system, or lightly chilled water through a system. It would pick up the heat on the heat exchange off of the system as it ran through, pipe up to the roof, blow off, come back down into, so basically you had an entire infrastructure that was this kind of closed loop system to cool off the systems. So then what we kept pushing, and LRZ is again a pioneer in this, is to keep pushing up the temperature. So to really reduce, to have as little chilling as possible, and to try to really use ambient water temperature. This works well for the most part of the year because there's enough of a delta between ambient temperature and weather temperature and the temperature of the systems. During particularly hot parts of the year, this becomes a problem. And then you have to move into chilled systems or chilled solutions. But for the most part, this can move forward. And again, this is an area that LRZ has really been pioneers for. And several of this technology, particularly with the Lenovo systems that we have that are part of the SuperMUC fleet that we have, they've taken that research that we've done with them during the procurement phase, or during the development phase, and they've been able to turn that around to commercialize it and then distribute that to other data centers and other entities. So that technology from Bavaria and that request and demand for energy efficiency has already been pushed out into the global market. So that's kind of on the cooling part. And then, of course, now we have the entrance of machine learning from our computing capabilities, and we immediately turned that around to start studying the systems that we had, to start being able to determine predictively where we could make adjustments to the overall workflows of the systems, and be able to do things like dynamic power down, dynamic adjustment, dynamic scheduling, all for the idea that once we have these systems turned on, they cost energy. And so when these systems are running, we want it doing as much compute as reasonable. And so we don't want lag time. We don't want delays. We don't want compute nodes to sit idle waiting to do something. We need to keep the scheduling. We need to keep those jobs going so that we are not wasting power, because anything that we're wasting is really, one, money lost, and it's science that doesn't have the opportunity to show result. So we take this very seriously. We have a very high uptime, and this is a constant tweaking and optimization problem that we address. Next slide. Okay, so this gives you a little bit of idea of the large energy infrastructure that we have, right? And so this may be familiar to some of you, but we have these cooling loops and these cooling concepts. We currently have, I think our inlet temperature, like the water going into the compute, is somewhere around 38. I think we could go up to 40 or even higher. So again, we're kind of pushing. And this is pretty warm. When the human body is about 39 degrees, this is a comfortably to maybe a little bit uncomfortably warm shower temperature. That's the water coming in, and then it comes out several degrees hotter at a very fast flow rate. And so this system, as I was mentioning before, the system is not just tubes running through the compute. What we're also trying to do is the cooling component. The tubes run past particular parts of the compute. What we're trying to do is get it to pass through all parts of the compute. That's another big goal, so that we can really optimize that heat transfer out. And then that's an area that we're developing. But then again, we're also continuing to develop the overall infrastructure that you see in these lower pictures. That's in the basement, that's up on the roof. So it's this entire large scale engineering infrastructure problem to cool these systems in order to be efficient and to utilize this energy well. Next slide. Okay, so I was trying to think through, and again, I was kind of reacting to a question that Emily posed to me. And this is a little bit sloppy notes because I was really trying to formulate in this in my mind. But when we kind of look at trends and kind of future directions that we're going with all of this. So again, exascale computing has been a significant push for us for energy efficiency. When we've got systems initially with the ECP program, we were thinking that the performance was going to be bound within a 20 to 30 megawatt power envelope. Now that has held true somewhat. The Frontier exascale class system at Oak Ridge runs at about 23 megawatt. The Aurora system at Oak Ridge is running around 30, or excuse me, at Argonne National Lab outside of Chicago is running at about 39 megawatt. Those were the official numbers from the top 500. And, again, it has to do with several factors. It has to do with the technology itself. It has to do with the cooling infrastructure. It has to do with the optimization in the scheduling, in the software infrastructure. It has to do with all these different components. But having the exascale program was one of those defined pushes that not only took us up to that level of compute, but also tried to push us into that energy envelope that we're dealing with. We also have things, again, like the innovative cooling solutions. Again, as I said, direct liquid cooling is becoming quickly, or not quick, well, it's becoming the standard. And when we look at companies, we have a lot of startups like in the AI space that are doing really good work on the compute part, but they're still working with like air cooling. And so we bring in systems as part of our testbed program where we have to provide infrastructure for air cooling or cold water cooling, but we have to tell them, look, you're going to need to move into this direction. So while you're advancing your compute, this is something that you're going to be thinking about in terms of your cooling, because we would not be able to sustain or host large scale technology like next generation AI chips, unless you conform to the infrastructure of the energy efficiency. So that's going to continue advancing as we go forward. Some large data centers are starting to look at immersion cooling, where it's basically kind of this oil that dissipates the heat out. So you basically drop these nodes into oil vats effectively. This is, frankly, I don't know any major large scale HPC centers that within the academic realm or the national lab environments that are doing that. I think that there's some experimentation with data centers, but I don't really know, and this might just be my ignorance, the maintenance and the operations of that and changing out nodes and all. There are certain cons to that approach, and I'm not really sure where it matches up to DLC method, but that is an area that's being explored at. In terms of advanced power management, again, the machine learning, the AI integration, we're using that to really study these systems. I'll talk about in a moment, but we really want to look at dynamic power management of systems because we really have to operate effectively that energy use in real time and account for the jobs as they come in and as they start coming from the queue into execution, how we adjust the systems, how we turn off certain parts of portions of nodes, portions of systems. How do we integrate all of that? That's a big thing. Smart grid is, of course, a big topic because we do integrate with smart grid technologies to manage supply. We do use green energy. We buy green energy, so we're trying to reduce our overall footprint, but we're still buying a whole lot of it, right? And so looking at things like smart grid, where we can do things like use renewable energy, have good battery storage, collect energy or collect power when the prices are low, when the prices are low, store it, be able to use it then when prices are high. That's all things that we're doing to mitigate costs. But again, we're still using that power. And so we still have to look at how to reduce it overall. And then, of course, again, as I mentioned before, this is still a changing ecosystem and evolving technology overall. So we're looking at new architectures. ARM-based processors are starting to gain interest in this space because of the potential that we have for effective use. We're doing that. And then, of course, the reason that we're here, quantum computing, we're looking at this very closely as another potential path to reduce overall energy consumption for certain types of computation. And then really trying, from an HPC perspective, one of the big questions that we have is that we acknowledge, and this is absolutely where we're going, to integrate quantum processors as accelerators for particular parts of workloads with HPC, but really kind of a question that is kind of in the back of my mind too is, well, quantum computing is not going to be great for all sorts of compute. That's a given. But even if the quantum computing, even if we could do something on HPC faster than we could do it on quantum. One question, and we're starting to set up these experiments, one question I have is, well, maybe it's not as fast on quantum, and maybe there's no reason for the compute part of it to put on quantum, but in the end, it has less energy overall usage. Maybe that's an argumentation. Again, these are kind of questions that we're now starting to explore because we have these quantum systems in-house. So if you could go to the next slide, please. Okay, the one thing I just wanted to make sure that I mentioned is that this all sounds great. All of this reduction, optimization that we're doing is great, and we've been doing this in the HPC space, and I think this is going to be a lesson for quantum as well. Certainly a lesson for AI processors and all. But the better that we get at energy usage per unit compute, typically is not that we have a certain amount of compute and we just reduce down and get better at the overall energy use. Basically, we get good at it, and so we just start doing more compute, right? We see that with the machine learning in the AI space and these large language models. I mean, that has just spiked everything up. But in general, because we get better results, better clarity, better resolution, more complexity of understanding of problems, more multidimensionality of problems can be considered, we're always going to be pushing that envelope of compute. I think that is just going to always happen. And so that is one of those paradigms that regardless of how good we get, I really do think that we're still going to be continuing to push the level. We talk about exascale now. Zeta scale is going to be the next topic once we get established in exascale, and we're going to keep going. Okay, next slide. All right, so now kind of enter quantum. So this is a space, so our department at LRZ has been around for just a bit over 2 years. And we started the strategic planning for this about 3.5 years ago, understanding that these systems were starting to move out of the physics labs. They were starting to move out of stealth mode in startups, and they were starting to become viable, one, access remotely, but then eventually, as it is now, they were starting to move into actual centers like ours, and to start to be available. So as we were looking at this, and this is a picture from Max Planck, one of our very good partners that we work with on neutral atom technology. This is kind of a starting space, and I put this picture in here always to remind myself that I start to think very operationally about quantum systems, about the efficiency, the operation stability, all of these things, but we really must consistently remember that this is still very early phase for these technologies, and so there's going to be a whole lot of rapid evolution, paradigm shifts at a space or at a pace that we don't have with HPC because we are more established. But as we're trying to integrate this in, as we're trying to think about the energy efficiency, the integration into the HPC environment and workflow, I have to always remember that these systems are still have a long way to go to get up to scale, to become stable, to have all the components that we need for what we would call production level compute. Next slide. Okay, and I know I'm preaching to the choir here, but I just put this in here to a reminder point. Several different of these qubit technologies have different physics constraints or opportunities or configurations. We are also looking at a diversity of engineering solutions. So, whether the synthetic or natural qubit foundation, whether the topology is star-based with great communication, or it's a linear together, the coherence times, they all have their own unique characteristics, and then the engineering that's required to operate them, whether it be cryogenic technology, whether it be lasers, cooled or uncooled, we've got all of these different components. So we're not, when we talk about quantum computing, and again, as an HPC center, that was one of the early lessons that I had to learn, because we started with superconducting, but we brought in ion trap, working with neutral atoms. I would love to be working with photonics. We've been bringing these cryostats into the ecosystem of our compute environment. All of these have a different characteristic, different needs, and different limitations. So that's something that is also a new challenge for us, because we have the relatively regularity of HPC systems, with the exception, as I mentioned before, of those next gen AI components. Next slide. Okay, so this is just a quick representation. I know that you all see this, I'm preaching to the choir, but we have right now several different form factors. So we've got the typical cryostat type looking environment, or a setup. We have, ones that are more proposed to be more commercially production ready type systems, like the upper left, the AQT system that's in the bottom right. I really appreciate, as an HPC center representative, I really appreciate that they purposely went into data centers and HPC centers early on in their design choices, and really tried to put this into standard 19-inch racks. Actually, those are a bit larger, but it's fine. But to put it into form factor that's more customized, or that's more regular and familiar to HPC spaces, so that we can implement them. And then also, when I look at like quantum brilliance, it's very interesting and intriguing that they went with a blade form factor where you can literally, that's a couple of U's, where you can shove them straight into standardized rack environments. So the compute is literally right next to the classical compute. So many different things. I always say that we're kind of building the saddle while riding the horse. With all of this, this technology is continuously advancing. At the same time, we're trying to implement it and bring it into a environment that our users can use it and start to generate initial results for their science. Next slide. Okay, so at LRZ, we have several different systems in-house or coming in-house. Right now, we have 4 systems, 3 in the superconducting line. So all 3 of these are from IQM, the Finnish-German company, a superconducting company. So we have 5 qubit and 20 qubit in our R&D space, and then we have a 20 qubit actually in our compute cube right next to our HPC systems. Also in our quantum integration center, which I'll talk about in a moment, we have a 20 qubit ion trap system from AQT out of Innsbruck. And we have, so this is a startup out of this region. And then we also have with our partners in Planck, which is a spin out of Max Planck, we have a neutral atom system coming in soon in a couple of years as that technology continues to advance and as they move out into commercial space. We also have, again, in the superconducting line, because that's where we started initially with all of this, and also where we're looking for some, for looking at the patterns of the scalability and all, we have a procurement out that is actually owned by the Euro HPC. And that is going to be a 50 plus and 100 plus system that'll be coming in starting in next year once decisions are made and announcements are made for who gets awarded the systems. So we have all of these systems in-house now. We're really starting to move forward and push. Next slide, please. Okay, but again, I want to come back to, I'm going to try to bring this back to the energy efficiency and just the general operations of these systems. The left-hand side, these cryostat components, these for us might as well be space aliens for an HPC center. It took us quite a bit of learning curve to understand how to operate these systems, how to maintain them. They're also as stable as Blue Force is in this work. There are requirements, the cooling components, the sensitivities of them overall. And so this has been really a learning challenge. Now, I used to like to complain a bit about the cryostat setup, and I'm also really excited to see Qtra in these presentations. I think they're doing a fantastic job. Also really thrilled to have another startup in the Bavarian ecosystem that's working to address, really head on address some of these issues with optimizing early on. I think that's fantastic. I think the whole field is kind of moving in that space too. I used to like to complain, honestly, a little bit about the systems on the left because they weren't really designed for HPC centers. But, there are new models coming out, like what you see on the right, that they're taking into account that there are going to be cryostat farms in supercomputing environments. And so they're really working to make things more compact, to make things more efficient, to make things more operatable by HPC technicians and facilities teams. And so the whole field is exciting that we're starting here. We identify problems, and sometimes we're already starting to work to problems, but then we find out that the problems are starting to resolve themselves, and then we can focus on other problems. So this is exciting field because everything is rapidly moving forward, both from the physics and the engineering part. Next slide. Okay, so to our quantum integration center. So this is a picture of the AQT system to the right, and then to the left is both the 5 and the 20 chip from IQM in the cryostat. You see kind of in the middle there, the thing with the 4 fans going down. That is part of the support compute for the IQM. And then what you don't see on the far right side, right to the AQT, that is part of our HPC testbed called Wolperdinger, because it is packed full of several different types of processors, GPUs, CPUs, some FPGAs, some SmartNICs. We basically loaded it up with everything that we thought we might be able to use, because what we're really doing here is this is our experimental space. This is where that we're really trying to test integration of quantum accelerators into HPC. We're setting up several different experiments in terms of workflow. This is where we do our software development, which I'll get to in a moment. And this is also where we're doing some of our energy studies and some of our sensoring and monitoring studies. Next slide. Okay, so getting to the monitoring, so I'm going to go back to the HPC space for a moment. So the one thing that we have, again, in terms of both operations and understanding where we can cut the fat on energy expenditure, we have a very pervasive monitoring environment established. We have what we call the DCDB, or the data center database. It takes thousands of sensors from the HPC system. It pulls it all into a common database. It pulls data coming from environmental sensors in the building, from any other, I'm trying to think of the other, for DCDB, it's the system sensors, it's the infrastructure sensors, there may be some other inputs, but it pulls those all together into a common database, and it allows us to work with it to be able to analyze it. So we run machine learning models with it. We learn to understand where certain trigger events are happening, where that we can be reactive in terms of maintenance, in terms of operations, but then also to understand like energy shifts, when certain applications or certain jobs are being run, how all of this works together. So this is one area that we've been very advanced on. Again, one of the forerunners in this sort of area, again, out of necessity. And this allows us to have some really interesting operational data analytics that we can use to help drive adaptation of the jobs, of the work, and of the use of the energy that we use towards our users' scientific pursuits. Next slide. Okay, then bringing it to the quantum space, we did basically the same thing now in the Quantum Integration Center. Now, what you don't see, well, actually, you kind of see a picture where it says temperature sensors. What we did is that we really just kind of went crazy on the IoT, and we basically over censored the integration center. We have easily 15, we have other ones coming in, types of different sensors. We have temperature like every 10 centimeters at multiple points around the room. We have humidity, vibration, electromagnetic radiation. We have sensors coming from the elevators down the hallway. It's like this whole cadre of sensors that we're putting in. So what we want to understand, I mean, we know that quantum systems are error prone, that it comes from the actual qubit manufacture and some for synthetics on its own. There are inherent errors that are propagated from the qubits, but then also the environmental surroundings play a big role. And so what we're trying to do is really understand all of that. Again, we pull all of that into the database. We have machine learning models that we're working on with that. And then we're trying to get to the point where we do predictive calibration, where we do predictive scheduling divergence for the users, because we don't want them, if a system is becoming less reliable, we want to pull them to another system, and we don't want them to have to worry or notice about it. So there's a big operations component, but then we're pooling that data as well with the HPC data. We're putting sensors over in the quantum computing, or the quantum computer that's in the compute cube, and we're pulling all that together so that we can really understand things. Now, this is the setup for the operations part, and we're doing some initial energy analysis, but what we want to eventually do, we want to understand the workflows and the impact of, or the energy usage on the workflows. The goal that we really have is to understand basically every second of compute that's happening on these systems, and then where we have optimization opportunities. That's a whole lot said. We're actively working on this. And the one thing I wanted to say is I'm excited to see this initiative, this quantum energy initiative. We have HEVI positions open. We also have the opportunity for PhD topics. If you're interested kind of in this space, really kind of the hybridization of quantum and HPC to address some of these questions, please talk to me, because this is an area that we really want to push forward. And just like we have been in HPC, we want to be leaders in this space as well. Next slide, please. Okay, so now I want to get to the software stack, because we've been addressing, components of the hardware, but the software is going to be doing the heaviest of lifting with the user, for the user component of this, and then also for things like determining and optimizing energy flow and generating of results. So we are definitely leaders in our systems software development. So we call this the Munich Quantum Software Stack. This is a hybrid HPC accelerator, quantum accelerator computing system software environment that deals with everything from the co-scheduling and co-resource management of the accelerators with the HPC, It also has the more strongly quantum-directed compiler that works with this entire ecosystem. And then we have a framework called this QDMI, this quantum management interface, that connects with several different backends. So what we've tried to do in a nutshell is that right now in quantum space, we're really requiring the users to program at the hardware level. In HPC space, the only people, we call them the bare metal people, they're the only ones that really don't even care about the system software stack, that don't care about anything. They are basically programming to the metal in basically assembly language, or sometimes even a bit lower. It's very generous to call where we are right now with quantum assembly level, because it's definitely lower than that. But what we're trying to do in our space is, because we don't have this abstracted software environment, we're really requiring our end users to program basically to the quantum metal. And that's not going to be sustainable. That will work for the physicist, for the raw physicist who have been using these systems as experimental, as experiments for their work. But as we try to bring this to more diverse user groups, this will not work. We want to try to abstract things up so that at the end of the day, our goal is that our users don't even really know what they're computing on. In some cases, the users will need to or want to know, but in some cases, they just want better results. And so they're not going to know, or they're not going to care that part of their codes are being offloaded to a quantum system. They're not going to care that we've made that decision because of energy work that we've determined that it might work better on the quantum than the HPC. They're going to be removed from that. It's our job to sort that out and understand that. So that's where our system software stack is coming in. We are leaders in this space. We've been working on this for a couple of years now. The first version is coming out this summer. And then from there, we're going to be expanding. Now, the reason that it's becoming, that we're releasing it, is because we've just seeded and accepted the QEXA quantum computer that's in our compute cube. Our AQT system is accepted and is about ready to go into operation for select projects. And now that we actually have these centers seated, established in our compute center, we have the foundational part of the MQSS set up. We have the infrastructure for the monitoring and the telemetry work set up. Now is where we've built the skeleton, and now we're putting on the muscles and the lipstick of all of this. So that's where we are with our evolution here. Next slide. I think I need to speed up quickly. Now, across Europe, so our center is, LRZ is great and wonderful and groundbreaking on many fronts, and we're doing really good work and we're having a lot of fun doing it. There are other centers across Europe that are getting to enjoy the same sort of experience. With the Euro HPC joint undertaking, this is a European level entity that has been responsible for putting a lot of supercomputers or HPC systems throughout Europe in these different centers. And in the last couple of years, they have included in their portfolio quantum systems. And so Germany, LRZ for Germany is the center that has been selected to seat a system. This is going to be that Euro QEXA that I mentioned before, the 50 and 100. That's going to come into our environment. And we're working with all of these other countries that are getting different technologies, from ion trap, neutral atoms, photonics. It's going to be this nice portfolio of systems across Europe, but we all have the same mandate. We have to connect quantum to HPC. And so we all have the same problem. LRZ, we are a bit further because we've been working on this from the get-go, because we had the mandate to have these different systems several years ago. But we're all working towards this. And so we're not only just working towards establishing these systems, making them available for users, but we also have to ensure that we're thinking about things like tight integration and what the benefit of tight integration means for us. Next slide. Okay, so again, I mentioned in kind of a little bit of a bragging moment, if you'll allow me. On June 18th, we had our official acceptance of this system. This is the QEXA system, 20 qubits. And you can see some of the compute behind it. We were successfully connected using preliminary elements of our Munich Quantum software stack. We successfully ran a job from our HPC system, our SuperMOOC NG, to the QEXA system, and then back with readout. This was one of the first times this has been done on two systems that are co-located in the same HPC environment on the same network, utilizing a hybrid system software stack. So this was a proud moment for us because we have the nuts and bolts now, and so we've moved from theory to praxis, and now we're going to be expanding our work. So one thing that we're doing is we're looking at benchmarks. There's been a lot of work on quantum benchmarks, a lot of work on HPC benchmarks. HPC benchmarks tend to be these these big assembly suites with several different domains represented. We have that established. We have really good proxy apps or kernels that are used throughout the community, standardized benchmarks that we can utilize. But on quantum, we're still kind of missing that. And so that's been a lot of work in this space. But now the one thing that we're really trying to push is that we need to have these end-to-end quantum HPC benchmarks. So LINPACK is no longer going to cut it. Honestly, whatever comes up for pure quantum is nice, but that's not going to cut it. If we're going to look at all of this, we need to be able to have an end-to-end quantum or HPC quantum offloaded and back type of run that has significance that then we can then use. And then we want to look at things like, what does that actually mean in terms of the energy? So is it, I mean, what is it, qubits per watt, flops per watt? How is all this going to work together? These are some of the things that we're actively working on right now. We have a couple of projects in motion, and I wanted to talk about some of the results, but our one person said, to hold off a little bit. But we're actively working on this space. And again, if this is something that you're very interested in, please come and talk to us, because this is going to be a heavy lift to kind of sort all of this out. Again, we're building the saddle while riding the horse here, but there's a lot of opportunity here for some interesting results, really working on praxis and not on whiteboard calculations. Next one, please. Next slide. So this is my last slide. Oh, I'm sorry, the slide before, sorry. There you go. Perfect. Okay. So then just kind of wrapping up, Emily also asked me about like areas for improvement that I saw. And so I was really trying to think about this a lot, even today, and I kind of came up with a couple of different thoughts here. But for one, I think as we continue forward, the holistic approach is going to have to hold firm. Quantum is still developing their technology, and it must, and there's a lot to do in that space, and so it must necessarily do that, but it needs to constantly have the eye on how it's going to be integrating into HPC, because the HPC is going to be able to handle its pre and post processing. It's also going to be able to help with some of the error correction components. There's areas that's going to be beneficial from the HPC side of the world. We're looking at quantum as a way to offload parts of very large scale compute problems. So when you think ideally and idealistically, when you think about things like climate codes or computational fluid dynamic codes, coming from a space like the Department of Energy or large initiatives where there are codes that are millions of lines long, we went through a porting exercise with GPUs to understand where we could take particular parts of a code that had a particular compute behavior and push it out to GPUs, and then to come back and be part of the whole ensemble. What we're looking at now is where could we take some of those? Is it going to be some of the GPU part, GPU to QPU? Or is there going to be some other parts, some other algorithms that get developed that could replace some of the HPC algorithms? We're looking at how we would be porting and offloading onto the QPU and sort of make that QPU part of that entire compute ecosystem in this heterogeneous fashion. So this integrated design is really important, from the alignment with the hardware, the communications, the networking, all of that, to the software design, to really ensure that these are working together very efficiently. And then again, as I kind of mentioned before, we need to look at the end-to-end optimization. So it's not just, tweaking these parts together and making the Legos fit nicely, but it has to be across the entire spectrum, that end-to-end. And the other thing that I wanted to mention is that there's going to be this, we need to understand, again, in this heterogeneous space, what is going to be this right mix of hardware use, and then how does the software kind of couple it all together? In terms of standardization and benchmarking, and I think there was a standardization talk earlier that I didn't get to participate in, but we want to look really at that, at unified metrics for understanding, how are we going to calculate energy efficiency across hybrid systems, and then how are we going to really make sure that they are comprehensive, that they are telling us what we need to know, that again, with respect to LINPACK in the HPC space, it does its job for a functional purpose, but again, it's kind of taken a bit of a political role, and it's become kind of a metric that it's kind of nice, frankly, for like chest beating. Yay, we've got this many, we're this fast, we can do this, we're the top of the chart. Is that really the most important thing? And so, right now, like in the beginning, it was the number of qubits, right? So we've got this many qubits and they have this many qubits. As we move forward, we want to make sure that we have benchmarking that is realistic and that is real and usable for the advancement of the science and the technology. And then the other thing that I've been thinking a lot about is everybody wants to get on quantum systems, right? Because they're the cool things and all. But what we really need to understand, and what we need to have our software infrastructure supporting us on, is being able to address the compute that is given to us, and seeing whether it is valid to run on those systems or not, or to run on the best system for the compute. So there's going to be compute that's going to be best for a superconducting or an ion or a neutral, based on the characteristics and the personality of the compute parameters, right? So we need our technology to be able to do that for us, and that's going to become important, because if we put something on a superconducting, okay, that's going to cost more energy than an ion trap system or a neutral atom system. So once we determine that, we want to try to push compute to the right environment, also kind of with that energy cost in mind as well. So we want to be selective. We also, in HPC space, we run things on clusters before you actually get onto the advanced hardware. And we do that so that you spend time optimizing before you go on to the big systems to run. We also want to look at the roles of simulators. So we have a nice relationship with Eviden right now in our Captiva, where they're emulating the quantum systems that we have, but they're making sure that it's updated. The parameters of the simulator are updated, not real time, but in a realistic tempo, so that our users can experience as close to reality as possible on a simulator, tweak their codes, understand what works, what doesn't, and then basically shift from the simulator over to the quantum in kind of a seamless fashion. So that's going to be important. And then the other thing that I really wanted to underline here is the cross-disciplinary approach. My team is, I have 35 folks on my team, everything from computer scientists to physicists to electrical engineers, all of these mathematicians. It's this cadre of people from different perspectives, and that's genuinely what is going to be needed here as we move forward. And so we need to have that relationship between the engineers designing the system, the computer scientists writing the software stack, the environmental scientist, understanding different parameters to kind of bring this all together for a very holistic, in this case, energy efficient solution as we're thinking through this. And then the other thing is just in general, we need to support an innovation ecosystem. This means that we have one that continues to foster and prioritize energy efficiency through funding, through these partnerships. One thing that is really important, and like what we did with the DOE with the purchase of supercomputers in the past, is that when you've got multiple procurements that we are all working together and we're all aligned, we can demand certain criteria, certain parameters together. And when there is that unison from the buyers to the companies will adjust and the companies will meet the needs. We've already have that happening in the procurements for the systems now, but as we move into energy efficiency and all, that's going to be one of those things too, that we want to require certain things as we move forward. Money is power, and we want to be able to help drive those directions. The companies, of course, going in that direction themselves, but sometimes they do have to make benefit cost decisions. And so when the money is there and when there's support there for that effort to be done, then they have less of a problem being able to go in that direction. So that was a kind of a bit of a whirlwind. I hope that that was interesting for you from the perspective that we have from the HPC space. Really looking forward and very happy that you're thinking about energy. I think there was the conversation of the point, is it too early or too late? I definitely think that it is right on time myself, because it's right on time without making sure that you cut yourself off from opportunities and potential. But it is really important because there's so much, like from our perspective, there's so much in the HPC environment that we need to couple in with the quantum environment. So for us, the fact that you're thinking about this early on, in some ways, we were late to start, as the last speaker mentioned very fairly. We were late to start to think about energy efficiency, but we have evolved and we've been moving forward and we've been putting priority in that space. And if the quantum is already starting to think about it in that realm, that as we're coupling together, we're in a good place, right? So in all for all, I think it's great what you're doing. Thank you for having me, and I hope that was interesting for you.
Okay, then thank you so much, Laura. That was a wonderful talk, and it's so relevant, as you say, just partly because of this integrated design that we're so dependent. Like quantum and HPC should be working together, and it's going to be a big part as well. But also that we can learn from it, as we saw from Ziki's talk as well, on the path dependencies, and exactly as you say, have this sort of like integrated ecosystem around it, which is exactly what the Quantum Energy Initiative is trying to foster here. That it really takes such an interdisciplinary team. So thank you so much for that.
Sure. And again, and I'm sorry, I'm not trying to peddle wares, but if anybody's really interested in this space, this is a very exciting space. So please do come talk to me. There are definitely some opportunities for some fun research and results discovery. So please come talk to me.
Hello, can you hear me?
Yes.
Oh, okay, yeah. So I saw the image of like where you had the quantum computers like lined up alongside the classical ones, and like so in a future where that does happen, like it's all working together like flawlessly. Um, you would have to like change the way you test these, right? Because like if you use the same like the LinPack test, like quantum
Yeah.
computers are really, I mean, they're much better than classical computers at solving like linear equations. So we would have to kind of come up with a new standard to even quantify how good your system is at that point in time.
Right. Yeah, exactly. You're exactly right. So there's going to be this real interesting opportunity for, and I mean, it's going to be, what is the metric? Is it's still going to be performance. Performance is always going to be a play here, but is it going to be kind of like the Green 500? Is it going to be performance per watt? Is it still going to be performance per time? Is it still going? What is the parameter going to be? But so we have the LINPACK for HPC, and like I said, there's quantum metrics, and they're not even benchmarks yet, metrics that are being defined for quantum. But when we put those all together, and then we put them all together with an actual application to be a bona fide benchmark, then what's going to be the standard there? Is it going to be, and I would actually, the one thing that I would really like to caution, and I gave a talk about quantum benchmarks, one thing is that we really should make sure that we see an ensemble of benchmarks, that it's not one benchmark to rule them all, but it's a suite based on several different parameters. I mean, we do that for HPC, but that really kind of comes in the procurement evaluation, not so much at the press release level, but we need to think about that. But you're absolutely right. And so that's exciting to think about, what is that going to be for the hybrid, but also then from the end to end based on a metric that actually matters, right?
Hi, thank you for the wonderful talk, first of all. I have a question regarding, I mean, you mentioned about the because superconducting qubits act in at a lower temperature, so they might have, to consume a large amount of energy. But other than that, like looking at the from HPC point of view, integrating quantum computer, quantum hardware in HPC labs, other than energy consumptions, what other parameters you have, like, observed, if you have observed with different platforms, like trapped ions, neutral atoms, or superconducting qubits?
So I mean, that's please ask me that again, like in a year, because as our systems are all coming up, we really only have very preliminary knowledge with the systems now being active and now being coupled together. So it's kind of early for us to give like really strong opinions in this space. But for us, I mean, so the energy is definitely going to be one of them, but for us, it's going to be, as these systems, as the quantum systems continue to scale, we have to look at the complexity of problems that we'll be able to address. We have to look at the latency. So right now in this space too, there's a couple of different approaches to integrating quantum and HPC. We call this, there's one that's kind of loose coupling, where that's basically determined that the quantum system can be like in one country, the HPC can be in another, and that right now, and it is true that right now it probably doesn't matter that they're so separated from one another. It could also be that different technologies may be okay with this loose integration, but then as we move towards tighter integration, so right now we're kind of in this middle phase that our quantum is on the same network as our HPC. It's, the software stack is all working together. There's a level of intimacy that we don't have with the loose, but where we want to move in the future is that we want the pipe dream, or the goal here, is that the individual nodes of a quantum system or of an HPC system, thousands of them, right? The individual nodes will be able to call off to a quantum system. So that's a tight integration that requires much more complex network infrastructure that does require like an on-premise proximity, and then it's also going to be dependent on the type of technology. And so this is the stuff I can't really answer yet because we're doing modeling of this. But one thing is this better suited for neutral atoms, and how the engineering and the physics work there? Is this better scalable for supercomputing? I mean, a lot of effort, a lot of interest has been put into supercomputing for this sort of model. And then as we move into thousands of qubits, how is the story going to change, and how necessary are these going to be tightly coupled together? And then I think it's going to be I think it's going to be the performance, it's going to be the communication, it's going to be the latency, it's going to be the energy. Those are kind of the standard ones that we have, and then there's probably going to maybe be new ones as we move forward.
Hey, so thank you again. Just on a question that was coming up earlier about the cryogenic side, it seems like we moved to the dry cryocoolers for the sort of ease of operability, but that there's the trade-off that it takes more energy. I think that's maybe a slight simplification, but in general, if you take it as that, then how's that trade-off for you as an HPC center? Would you be willing to move back to sort of liquid cryogenics with all the sort of the overheads that comes with, to save on energy, especially as this sort of scales, if that makes sort of the difference of going from maybe 1,000 kilowatt hours per week to just 10, or how does that seem in your
That is a really great question. And I was just having a conversation 2 weeks ago with someone from out of Chicago. And I mean, they were talking about designs of like not just cryogenic systems like for a couple of qubits, but they were talking, or a couple of QPUs, but they were talking about like whole cryogenic rooms, whole cryogenic centers for like large scale QPU operations. And they're talking like cryogenic rooms. They're talking about facilities at like 100 megawatt or more. And so for me, I mean, it's kind of a question that I'm kind of shaking my head because I don't really know what's going to hold. But in general, I mean, the one thing too is that we do things like we power down part of our HPC nodes if they're running idle, right? So the one thing that I would like to know is, do I always have to have a cryostat on at full cold temperature, right? Because you have to get it down to a certain level in order to operate. But is there technology, or can we craft QPUs in a way that we can power up and power down when we need in order to save the energy? Because right now I'm running cryostats 24/7, right? And so what would be interesting is if I do have downtime on my usage and I've got less jobs, and if I've got a quantum farm of QPUs, can I send the users to other systems, and then can I power down those systems without affecting the QPUs? I mean, I think it's possible, right? But it's kind of like the powering up and power down. So that might be something interesting for the technology itself. And I would like to see where that would go. So that kind of dynamic scale, or that dynamic operations would be interesting for me as well. Did that kind of answer your question, or did I punt?
Hi, Laura, can you hear me?
Yes.
Okay. Yeah, so on this, so what we have done, for example, we have built a small IoT kind of device, which we call a compressor control unit, so CCU, where we can actually remotely just turn off and on our compressors, right? And then, so that was just a functionality that there's more old school compressors usually didn't have, so it was a kind of an easy task to do. That's one way, and of course you're talking about the power on a particular cryocooler or a particular system. So that was shut off the compressor, right, that runs the cryocooler. But of course there are also people I think investigating the frequency of the cryocooler, of the cryopumper, to also change the cooling power. So when we think more about system design and in terms of really having an optimized system that you maybe would do, for example, in outer space missions, right, where you have a certain energy budget and you are very keen on how to use this. So far, cryogenics was more like just turn it on and you have a lot of energy available, just use it. But we see and we think that there must be more systems engineering approach to cryogenics as well, to see the full picture, to see also parts of the components being able to shut down or drosseled in a way within operations. So yeah, people are thinking about that, and it's a question of time, and also of pull also from customers actually wanting something like that. So that's so if we know about that requirements, that's definitely can be also a driver.
Right, and I'm assuming this is Tomek from Kyutra, correct? Are you from Kyutra?
Okay, I will just forward the mic to another question.
Hi. So I just want to bounce back on what you just said, because actually it's very related to what I presented this morning, in the sense that so one thing is indeed you can turn off and turn on the computer when it's not used, but even you can, for instance, tune the qubit temperature for the task you want to do. Because so basically what is so as you know, what is hard in a computer is that it gets an answer that is the good one, and you can do it by doing more or less error correction. But there are many other parameters you can play with dynamically. So you could imagine that if you implement algorithm 1, then you modify the temperature of your qubit because you can handle more noise because the algorithm is smaller. But if you implement a very demanding algorithm, then you need your qubit to be very cold. So that's also something that we looked at. Actually, there are many things you talked about holistic approach that are very related to what we looked at also. So
interesting. And I'm sorry, I didn't catch your name.
Marco Felus Asiani. I presented the benchmarking this morning.
Oh, okay.
And also a scientific paper which is precisely about holistic approach for energy.
Okay, Perhaps we my email is showing on the slide right now. Perhaps we can connect as well. That would be really interesting. But yeah, I mean, the thing is, we've got, in an HPC system, we've got thousands of CPUs, we've got thousands of GPUs. I mean, the thing is, right now, just because of the scarcity of these quantum systems, we only have a couple, right? So I mean, we're one of the leading centers with like 7 systems either in or coming in. But eventually we're going to necessarily need to have like farms of quantum systems. We're actually building an extension right now where we're accounting for that. But then again, like as you said, just like we power down certain nodes and all that, we want to be able to power down, or I mean, what you say is very interesting. If maybe some of them go to a warmer temperature for certain types of compute that has been, analyzed and profiled, from something like the Munich Quantum Software Stack, that we then know that it's going to go to a warmer compute, then we would, we basically prepare the systems and then have the job in the scheduler and then run on that. I mean, that's a very interesting premise. It'd be interesting to talk to you a bit more, because that's also part of the operational design of how we integrate all of this together.
Yeah, sure. Thanks. I agree.
Yeah. Then thank you so much, Laura. That was really a fascinating talk, and I think I could honestly keep asking questions, but I think we should let Philip talk so he can make his train still today. But thank you so much. And I think PushQuantum organized a tour of the LRZ facility, I think one day before I got back to Munich recently. So I'm extra upset that I couldn't make that, but hopefully.
Well, Emily, just send me an email and you're always welcome over. No problem. So thank you all for having me again. And sorry again that I'm doing digitally, but thank you for having me.